Welcome, everybody. This is the Anesthesia Workstation. My name is Noah Dagan. I am a bachelor prepared nurse and a current SRNA. So, today we're going to be talking about points of failure and gas flow throughout the machine. We're going to be talking about the supply, processing, delivery, and disposal model. So, by the end of the day, the objective is that you'll be able to distinguish when these components are malfunctioning and how to resolve them. I'll signify that with a little orange smiley face and some notes. You'll be able to order and outline the flow of gas through the machine as we go through step by step. And then by the end of the day, being able to match the components to the correct conceptual model, either supply, processing, delivery, or disposable, will be easily, because I'm going to display that on the bottom right hand of the screen of each slide. And then being able to classify the correct pressure system in which those parts are located, I'm going to make that easy by just using different shades of green with my arrows. So we will see high pressure systems in dark green, intermediate, and low in those other shades. So what could you review before this lecture to help your understanding? Apex has a great anesthesia review, Unit 6 on the entire anesthesia machine. Those lessons there I've laid out are about 5 to 7 minutes each, so it should only take an hour or two. Also, University of Detroit Mercy's anesthesia program has a great introduction on the anesthesia machine components and systems, so I'll include a link and the credits at the end of this. And if you want a deeper dive, you can skim General Electric Healthcare's guide to their anesthesia machine. They have a long document that shows pictures and great information on their entire machine, so you can get a really in-depth view of an anesthesia machine. So, order of events, we're going to go through pipeline and tank all the way to the patient, step by step, slide by slide. I'm going to break it up. Throughout, you'll see that those little prompts in the bottom right hand of the screen to talk about that SPDD model. And then throughout, again, we'll talk about those components prone to failure. So the gas flow from the source to the patient will start with the cylinder. This is the supply portion of the model. They come in tanks starting at a PSI of 2200. Now, a PSI is about 70 centimeters of water, so it's a lot of pressure. Now, a cylinder, before it reaches and is down regulated to a safer working PSI, is attached to a pressure gauge. And now in our newer anesthesia machines, this pressure gauge is electronic, so we can see the current PSI, which tells us the length that the tank has left of use. Now, the primary source of oxygen that we use is pipeline pressure regulated by the hospital, and that comes into the manifold at a PSI of 50. Now, that too has a pressure gauge that we can see and sense if it's failed or not. Now, this manifold has two unidirectional mechanical check valves, and now what this does is the higher pressure that is received by the check valve is going to either open or close that check valve. So since the pipeline pressure is higher, it's going to open that check valve and close the check valve of the cylinder. That way, the cylinder gas is not used and it's saved. And ideally, your cylinder should be closed. So if we were to have a pipeline failure, either it becomes disconnected or the hospital's main pipeline pressure goes down, that valve will close. And if your cylinder is open, that check valve for the cylinder will open. So, orange smiley here, something we can fix. If your pipeline pressure has failed, your next response would be to go and open your cylinder if it's not already open. Ideally, it should be closed. So from that manifold, you're going to have an outlet to the rest of the machine, and we'll see that in the next slide. But on your way up from that, you're going to have a relief valve that opens around 100 psi, and that's to protect the components from damage. So if one of these pressure check valves were to fail and extreme pressure enters the machine, there is a release valve to protect the internal components of the machine. So we can see in the dark green of the cylinder, that's our high pressure system. And then as we pass that and down regulate to a more normal 45 or 50 psi, that becomes our intermediate pressure system. Now here's another example from Anesthesia Key that shows the same model that we've laid out here. You've got your cylinder gauges, your relief valve, your pipeline check valves, and your cylinder regulator. All right, so now we're going to move up. This is continuing from the relief valve. And now we're going to enter the processing. This is what does the machine do with the gas as it enters the machine. Now, with oxygen, there are 4 different areas in which it's going to go to kind of help the machine operate. So the first place the oxygen PSI is going to go and supply is an alarm. Now, as that pressure decreases either from a pipeline failure or emptying of this O2 cylinder, it's going to signal a supply alarm at around 35 or 40 psi, and that's going to be an indicator on your screen that either my pipeline has failed or the tank is empty. So what I need to do is either replace or open the tank. And then another thing to ensure is that the rubber gasket, when you put your cylinder on the yoke, is applied, because that will cause a leak. And if the leak is present, then you won't have a constant pressure supply. So the next place oxygen supplies during the processing portion of the model is the O2 flush valve. Now, before we get into that, normal anesthetic gas is picked up by the vaporizer through this low pressure system. It'll either go to the inspiratory limb or through the common gas outlet. Now you can close off your inspiratory limb and open the common gas outlet, let's say to add a nasal cannula. But as this pressure butts up against the O2 flush valve, we can open it and cause a flow of 35 to 70 liters per minute with this PSI of 50. Now that is much higher than the lower pressure system, and so you have to be careful for barotrauma as we open that flush valve. Now, something to note in this near the inspiratory limb is that there is a pressure sensor. And that pressure sensor is commonly used during the circuit leak test. It monitors the closed pressure system. And so if the circuit were to become disconnected, either be leaking from a hole or ever occluded, that sensor would pick up and alert the provider. So what we could do is either replace the circuit, reattach the circuit, or fix the occlusion. If the breathing bag or the reservoir bag was punctured or missing, that pressure monitor would also alert, so we could replace the bag. Later, you'll see the soda lime canister. If that gasket isn't completely sealed, that could mean we either need to replace the canister or reseat the canister if it's not fully clicked in. And then there are also unidirectional flutter valves, like on the oxygen in the manifold, that if they become stuck, need to be fixed or replaced, and that might require more maintenance, and you might have to get a completely new machine while that anesthesia workstation is being serviced. So here are some more models from Anesthesia Key describing that common gas outlet and flush button. So if you were to press that, you'd bypass the low pressure system and add from the intermediate pressure system. Here again, you have your relief valve and another image of what that might look like. So the third use of oxygen pressure is to maintain or prevent a hypoxic gas mixture. So just like the oxygen system, in the nitrous system, we have a pipeline, we have a cylinder with a regulator, a manifold with unidirectional check valves, and pressure gauges. Now, that is kept open by a constant O2 pressure, PSI of 50. Now, in the event of a pipeline failure or a depleted cylinder tank, that pressure is going to decrease, let's say to 20, and that will pull back a stopper that will prevent nitrous from continuing forward into the intermediate system, which will prevent a hypoxic gas mixture and delivery of nitrous alone. All right, so for the fourth use of oxygen pressure is we're going to see how it supplies the flow meters. Now, in an older system, you have Thorpe tubes, which directly display with a floating bobber, and in the newer systems, it's all read out on a digital display. So as oxygen reaches the flow meter, you have a control knob that's just attached to a needle, and that needle either is depressed or opened, which controls pressure from the intermediate to the lower pressure system. So as you open that system, you allow more oxygen to flow, which raises your flow rate, And we move from a PSI measurement to a liters per minute. And that's what helps us control the concentration of oxygen. Every increase in liter is about 4% increase in concentration of oxygen. And that'll be fed into the vaporizer, which we'll see in a second. So in the older models, we had to calculate oxygen concentration in our heads, and it was either attached with a chain to the nitrous system to ensure that there wasn't a hypoxic gas mixture. But in these newer anesthesia machines, there are electronic mixers which take in that air system and take in that nitrous supply, and they use Dalton's law, using the sum of partial pressures to deliver a safe concentration of gas to the vaporizer to then pick up the volatile agent. Now, one other thing to mention oxygen's use in the anesthesia machine is the use of a bellow. Now, in certain machines, they have pistons, which don't require oxygen to operate. It's electronic. But in the bellow system, oxygen is required. So if the bellows aren't inflating and are depressed, then it may mean that there's failed pressure delivery to that part of the machine, or the part of the bellows are dysfunctional or broken. So that might be a situation, again, where you need to discontinue the machine, have it repaired or serviced. So here's an overview of everything we talked about. We've got the supply. This entire system is the processing. You have your nitrous system, which is a small version of this. It's the exact same. And we end at the inspiratory limb, which begins the delivery system. Now, the delivery system is based on what kind of model you're using. Are you using a circle or a closed system? It also is dependent on your ventilator settings, your timing IDE ratio, or your respiratory rate. The delivery system also takes into consideration the monitoring, so the inspired and expiratory volumes. And here we can see some more examples of that entire model on a different graphic. We've got the high pressure system, the intermediate pressure system, and the low pressure system. Now, these models don't display the disposal part of the SPDD model, which we'll talk about here in a moment. So attached to the expiratory limb on the way back, we have the disposal model. This is where we start with the gas collecting assembly. Now, this is somewhat attached to your APL valve, so the pressure system is still intact here, which is why that CO2 absorber still plays a role when talking about supply alarms. Now, from the gas assembly, you have your transfer tubing, and that transfer tubing goes to your scavenging interface, which is your CO2 absorber. And from your scavenging interface, there is more assembly tubing, which is hooked up to a suction system within the hospital, and then it is pumped out safely to the atmosphere according to standards. So that was the anesthesia workstation, or at least part of it. There's a lot more detail that one could go into, but hopefully you were able to distinguish which parts of the anesthesia, some of the parts of the anesthesia machine that were, if malfunction, you could intervene and repair. Also that we were able to order and outline the flow of gases throughout the machine and match those components to that SPDD model using those indicators on the bottom right hand of the screen. And then as we went through those correct pressure systems, that you were able to identify what part is attached to the high, intermediate, and low pressure system. Here again are some of those resources: Anesthesia Key, the Apex Anesthesia, the University of Detroit Mercy's Anesthesia Review, and then of course your standard anesthesia resources, Barish and Miller.